Okay, I think we've just started now. Thank you very much. So there was a full start there. Sorry for being a few minutes late, but you're welcome, everybody, to this lecture of the John Chappell Natural Philosophy Society. I shan't call it a chat, because the chats are what we have every fortnight. We'll be having one next week, for example, where it's a more conversational format where we have everybody talking about particular subjects in science, contemporary science, or maybe dissident science. But these are more technical sessions, which we're hoping to hold every fortnight, where we give an uninterrupted session of maybe up to an hour and a half for the speaker to talk and give his presentation. And then at the end, there will be something like half an hour, perhaps, to engage in question and answer. Now, when I say uninterrupted, there will be a possibility for some immediate questions. You know, if somebody finds that he doesn't understand what the speaker has said, or he uses a word that he didn't understand, or he asks them to repeat something, he could just put maybe a comment up on the comments, or maybe if you're in the green room, just wave your hand and I will give you an opportunity. But Bob has indicated that he doesn't mind being interrupted for a very short period of time during the lecture, provided it's a very specific a point of clarification that is required. As I say, there will be a fuller session at the end. Now, this, to a certain extent, Weber electrodynamics and unipolar induction is a continuity in some respects of the subject of unipolar induction, and indeed induction generally, which was started in the recent format by Harry Ricker some weeks ago. And he's given two sessions. The last session actually was last week. Now, so he's been talking about the problem of this 170-year-old issue with Faraday's laws and Maxwell's equations and alternative forms, all the experiments that have been done by Müller and Kelly and all the rest. And Weber electrodynamics, introduced by Wilhelm Weber, to give everything its German pronunciation, was roughly contemporaneous with the work of Maxwell. Excuse me. And Dr. Robert Gray has made it a speciality of his to study the work of Weber, which the basic equation actually is just simple. It's a simple sort of Gaussian equation, but then the mathematics can be a little complex after that. So Bob will be giving us an introduction to that and comparing it with maybe the more conventional Maxwellian electrodynamics. And then he will be applying this to unipolar induction and seeing whether adoption of some of Weber's concepts can mitigate the problems that seem to arise, paradoxes with the various forms of relative motion in the unipolar generator, or the generator where the disk is separate from the magnet, and any of those magnet, disk, and or circuit or spinning. So you have two possibilities times 3, it's 2 to the power of 3, 8 possibilities. Now, let me see, Franklin, who is very kindly co-hosting this with me from the technical point of view. And I actually said earlier, and nobody has heard this, but I hoped he would keep me on the straight and narrow. And he actually did do that, because I hadn't started the broadcast. I thought I had started it and I was speaking and only a few people were listening to me. So Franklin obviously corrected that, and we've started again. I have a question: how to get into the room to join the conversation? Well, there is room in the green room. It's live.naturalphilosophy.org, isn't it, Franklin? If you want to get into the green room. Otherwise, you can get in through Facebook or YouTube. So that's Jerry Harvey. I hope I've answered. You're on Facebook at the moment. Okay. Now, those are all the preliminaries I think I have to engage in. And so what I'm going to do is I'm going to suit the action. Yes, Franklin has put it up, Jerry, there. http://live.naturalphilosophy.org. But we can only have up to 10 people in the green room. And the green room will have the advantage of allowing people during the question and answer session to come in and maybe give a little spiel about their own take and then interact a little. So we certainly can take a small number more in the green room. But if you're not prepared to do that, the preferable way would be to log in via Facebook or YouTube. If you have any questions, please enter them in the comments. Yeah, that's true. Even when Bob is speaking, if you want to add questions in the comments, Franklin or I will try to answer them. So without further ado, the floor is all yours, Bob.
Wow, something just cut out. Just as you were saying, without further ado, your mic cut out. So
that was deliberate. So I'm cutting out now.
Okay, very good. Welcome everyone. So Weber Electrodynamics and Unipolar Induction. I have a few more slides than I originally intended, which means I'm going to have to talk a little bit faster than I wanted to. Hopefully it's not too fast. The presentation topics, as Ian mentioned, I'm going to do a little introduction to Weber Electrodynamics to develop the mathematical model for a unipolar system, and I'll show how it resolves a unipolar paradox and clarifies two misconceptions that I often hear when people talk about unipolar systems or unipolar generator or the Faraday paradox. Then I'm going to propose, yes.
Just as a little hint, you can get rid of that little stop sharing banner by clicking hide there, so it doesn't obscure your slides.
Didn't know everybody could see that as well. Thank you very much, Franklin. Okay, so then I'm going to propose what I consider a very fundamental experiment to help resolve some of the issues. The experiment will have no closed circuit path. There'll be no lead to measurement devices, and it should be able to distinguish between the Weber and the Müller and others theories. Then I'll review Müller's 4 different setups and his experimental results, and then we'll have some discussion times. So why Weber? Somebody needs to mute themselves. The question, why consider Weber electrodynamics? Because I find Maxwell electrodynamics to have conceptual problems. The foundation of of Maxwell's electrodynamics is not clear to me. And as I say, there's other conceptual problems that I stumble over in Maxwell's electrodynamics. And as Harry actually mentioned last week, Einstein mentions this in his 1905 paper that introduces special theory of relativity, where he wrote, first sentence, it is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. So even back then, Maxwell's electrodynamics had problems. Another reason is it's not just Maxwell's equations in Maxwell electrodynamics. They adopt a force equation, this Lorentz magnetic force term. And I have questions about this force equation. I've read about its history, and I'm not sure that it's applicable in any case other than if you have a closed circuit. My understanding is that this came in part from integrating Grassmann's force equation around a closed circuit. And if that's the case, well, then it's only applicable to closed circuits. But anyway, there are questions about the meaning of the velocity v, which what this is with respect to. Now, Assis writes, unfortunately, Lorentz did not specify in the above equation what is the object, medium, or system relative to which the velocity v of the charge q is to be understood. He goes on to write, on the other hand, nowadays we utilize the expression with v being the velocity of the charge relative to an observer. And this change of meaning happened after Einstein's work in 1905 on the special theory of relativity. So, the meaning of these things seem to be changing. So to me, it's not a real great foundation from which to start and build uh, theories of physics. So as an introduction to Weber electrodynamics, an alternative, I find the foundation of Weber much more appealing, much more logical to me, even though I acknowledge that Weber electrodynamics is not the answer to everything. Weber electrodynamics is really good in a certain domain, and outside of that domain, it's questionable or even doesn't work at all. But within the domain, particularly what I can call classical electrodynamics, it seems to work very well. So here, I'm going to start with very basic and build up the theory for unipolar induction using Weber electrodynamics. And I'm going to start with Occam's razor. Do not admit anything into your theory that is not necessary. That's the way I think of Occam's razor. And we'll use that later in the presentation, but keep that in mind. Start from fundamental facts. Proceed in logical steps to build up a mathematical model. So I consider fact number one, charged bodies exist, electrons, protons, etc. What they are physically is not addressed. That is very unsatisfying, I understand, but that's where I'm starting. Fact two, one charged body causes a force on another charged body. How that physically happens is not addressed. Again, very unsatisfactory, but for the domain that I'm working in, that's okay. Okay, so next step. Based on experiments done by Ampere and Weber, the force on a test charge body due to a source charge body is adequately modeled by Weber's force equation, given here. Can you see my point? Yeah, Q gamma E, E superscript C, where QT is the charge on the test body and EC is the Coulomb field given by an equation we all know. And gamma is the Weber dynamic coupling coefficient. And I'll explain more about that later. Essentially, it mediates the force strength, the force on this test charge body and this strength of the Coulomb field. Since the experiments of Ampere and Weber were that of classical electrodynamic systems, not at the quantum level, in which the parts were near each other and there were no components traveling with respect to one another close to the speed of light, then it needs to be recognized that this is the domain of applicability of Weber's force equation and electrodynamics. So it's not necessarily the answer to everything, but within this domain, based on the experiments of Ampere and Weber, it is very good. Attempts have been made to extend this domain of applicability. Particularly, I've seen attempts by J.P. Wesley and Thomas Phipps. And we do not need to extend this domain for the topic of unipolar systems. Now, that dynamic coupling coefficient, what is that all about? Well, specifying the dynamics of mathematical terms, that is vectors, requires explicit specification of a coordinate reference system. All vectors, quantities must be based on that coordinate system. That eliminates this question about what is the velocity with respect to? Is it with respect to the observer? Is it respect to the wire that's in motion? Is it respect to the detector? Is it no? All the vectors are with respect to the arbitrary coordinate system that you pick for your mathematics. The dynamic coupling coefficient is then given by this 1 minus a kinetic energy like term and a potential energy like term. And I say like because this is, let me see, these are the actual mathematical expressions for it. And as you can see, this is 1/2 a speed squared. The dot means with a derivative with respect to time down here. And r times an acceleration. So this is kinetic energy like if I had a mass in here, that would be a kinetic energy. And if I had a mass in here, that would be a potential energy. For example, mgh, gravitational potential energy, m a mass, g an acceleration due to gravity, h a distance. Well, here we have an acceleration, we have a distance. If I put a mass in here, then it is a potential energy. So I call it kinetic energy like, potential energy like terms in this coupling coefficient. Okay, so from those basics, we build up a mathematical model. What we're doing is we can build up a mathematical description of electrodynamic systems from the above concepts plus idealizations, approximations, and the superposition principle. That's standard procedures in physics. For example, I start with an Amperian current element, ACE, is a differential in size current element, picture of it down here, that is charge neutral such that positive and negative charges are at the same position, obviously an approximation, and the relative velocity of the two charges is not zero. So the velocity of the negative charge could be zero, or the velocity of the positive charge could be zero, but not both. If it's both, then or if they're exactly the same, then they sum to zero and there is no current, right? So let me see. And all of these are in vector notation with respect to the coordinate system that you choose. So from that concept, we build up to a current carrying wire. For the physical situations to be considered, we assume that a current carrying wire can be approximated to be composed of Amperian current elements. Now that's not always valid. In particular, when you have AC currents, for example, and even with DC currents, I hear there's an accumulation of surface charges in real conductors. And we're going to do an approximation that we're not going to pay attention to that at this level for this particular application. And so here's a picture of a conductive wire. Where's my mouse? There it is. Each one of these little rectangles is supposedly representing an Amperian current element. And to determine the net force on the test charge, net force, sum all of the forces on the test charge bodies due to all the charges in all the ampere current elements comprising the wire. That's the sum. Okay. So if you go, I'm going to go back a few slides. So this gamma, as I say, is really this expression here. Okay, it has these three terms, the kinetic energy, potential energy. And if you stick these definitions in, you can write it in terms of velocities of each of the individual particles. And when you do that, you can collect the terms and it can be written out like this. That's a lot, okay? But I kind of grouped it, so hopefully you can see some patterns. Like in each one of these terms is the Coulomb force, okay? Then the next term here is really Ampere's force. That's Ampere's equation. Okay. Then you have a velocity of the test charge, velocity of the test charge. Well, that's velocity squared. You got a 1/2 out here. That's this kinetic energy like term. And then a kinetic energy like term for the sources. And then the two potential energy terms, one for the test particle, one for the source. And each one of these, again, has the Coulomb field in it. Okay. Now, the sum over all those ampere current elements and the charges within each one of those ampere current elements is not easy to carry out for macroscopic objects, even for idealized conductive wires. There are just too many ampere current elements to sum over. So we resort to changing the summations to integrals, and we use the vector calculus. And this is what that looks like. We replace the charge with a charge density, and we're integrating over all the sources. So now we'll go back to that current carrying wire, and instead of the summations, we're doing integrations. When the wire extends to plus or minus infinity, we can mathematically simplify the above force equation and get it down into this format. Some of the terms cancel, some are simplified. So we're getting closer and closer to something that we might actually be able to understand. So when the wire is bent into a closed circuit, CC closed circuit path, there's a circular loop, for example, the integration becomes an integration around that closed circuit path. So now the integrations are around closed circuit paths. Okay. And if you notice this term in that equation, here it is, I went back a slide. This term, that looks awfully familiar from Maxwell electrodynamics. We can take the term here, this integration, and call it an Amperian magnetic induction function. I call it a function, not a field, because there is nothing in this development to require or even suggest that this is a separate physical field. It is just a mathematical term in the Weber force equation for this special case. Okay, but yes, I'm going to use the letter B. I'm going to put a superscript on it for Amperian because this is not exactly Maxwell's electrodynamic magnetic induction field. And it's not in particular because I'm using Amperian current elements. And there are restrictions to the equation when you do that. Okay, so here, for example, I'm writing B. This equation can also be written like this, where notice that's the Coulomb field. E superscript C is the Coulomb field. So really, there's only this Coulomb field. There's not a magnetic induction field. Occam's razor again. Remember, keep that in mind. Do not admit anything into your theory that is not necessary. I don't think a magnetic induction field as a physical field is necessary. Everything in Weber electrodynamics is based on this Coulomb field. Okay, now we have the current carrying wire in a loop, a closed circuit loop, and it can be written, the force equation now can be written like this. And we'll be able to simplify that even further in a minute. But hey, look, QV cross B. But the B is Amperian, not Maxwell. We know exactly what this velocity is, V sub t. That's with respect to the arbitrary mathematical coordinate system that we have selected. Okay, so now I'm going to break just a little bit and talk about unipolar system the way I look at it. So the unipolar system will consist of a cylindrical circular shaped magnet and a circular disc shaped conductor where the magnet and disc are face to face and share a common rotation axis through their face centers. The magnet and separately the conductive disc can rotate about the common axis. So this is the setup. And what I'm particularly after is the force on this conduction electron in this conductive disc. And that's what the Weber electrodynamic equation is going to give us. So what do we want to know? the fundamental question is, what causes the force on the conduction electrons in the conductive disk? And that's simple. That's this equation that we started with, okay, Weber's equation with a coupling coefficient to the Coulomb field. That is, the force on the conduction electron in the conductive disk is caused by the relative dynamics of the test charge body of the Coulomb field associated with each individual source charge body in the magnet. This force, when it exists, causes a charge separation in the conductive disk and thus a voltage difference between the inner region of the disk near the rotation axis and the outer rim of the disk. But how are we going to model the actual magnet in Weber electrodynamics? We use the approximation that the magnet is composed of Amperian current elements forming closed current loops, and that this can be approximated by a closed circuit current loop around the perimeter of the magnet. And that's really based on Stokes' theorem. Here's pictorially what I'm talking about. Here's the magnet, this gray circle. In the gray circle are little Amperian current loops, okay? And if you look, you get one arrow going down and adjacent to it, one arrow going up. They cancel. One arrow going to the right, adjacent arrow going to the left, indicating current elements here. They cancel. Everything cancels except for at the perimeter. I didn't fill in all the perimeter, but you get the idea. Only these arrows are at the perimeter survive. They don't get canceled. And so I'm replacing the magnet with a idealized circular current loop at the perimeter of the magnet. And that mathematically is related to Stokes' theorem. So in his book, as this is reference and justification for that approach, in his book, Ampere's Electrodynamics, Assis writes, Ampere then concluded that a definite electrodynamic solenoid is equivalent to a long, thin, and curved magnet, provided the magnet and solenoid had the same shape with north and south poles of the magnet located at the extremities of the solenoid. Now, I've seen other references that Assis gives about Weber's writings where he says Weber says something similar, that in his experiments he's been able to replace solenoids and circles of wire with magnets that they seem to have the same effect on electrical systems. So that's the model, the mathematical model that I'm trying to come up with, a conductive disk with a wire as an approximation to the magnet. And the wire can rotate and the disk can rotate separately or together. So we have now reduced the problem to finding the force on the conduction electrons in the possibly rotating conductive disk due to the current in the possibly rotating closed circuit loop. We have an equation for that, which we developed earlier. That's this equation again, where the integration's around closed circuit loops. We assume that the difference in the acceleration of the two charges comprising the Amperian current element, the acceleration of the electrons and the acceleration of the charged ions, of the closed circuit loop is so small that this term can be dropped. I did a calculation once for the velocity of electrons in a wire, conducting wire, and man, that stuff is so small. And disregarding resistance for the moment so that we don't have, you know, a lot of acceleration. Just the order of magnitude here is so small, you're not going to see that effect. And that's kind of a problem that I've come across in Weber electrodynamics before. You do all this math, but then you start putting numbers into the resulting equations, and you find the terms are so small, you're not going to experimentally be able to see it. So anyway, I'm dropping this term involving the acceleration of the source particles. We can show but it's a long derivation that the second term in the force equation can be written in terms of the Amperian magnetic induction function. And so I just went back a screen. So this term here with mathematical manipulations, I'm glad to share with anybody that really wants to see it. We can actually write that in terms of this this magnetic induction function B, and that's what it turns out to be, this 1/2 Q, this V plus V of the sources cross B. So we've gone from this equation at the start down to this equation involving the magnetic induction functions. But we want to write this in terms of rotational speeds, because either the disk is rotating or the magnet is rotating. It's all in terms of rotation. So using cylindrical coordinate systems, we're just replacing the rectilinear velocities with rotational speeds. That's the rotational speed of the disk. We got the rotational speed of the magnet, which is now a closed circuit wire for this particular model. But we note that in our model, the current electrons in the closed circuit wire rotate at the rotational speed of the magnet, that is the rotational speed of that closed circuit wire, plus the speed of the current, that is the source's conduction electrons, when the magnet is not rotating. So that velocity of the electrons in that closed circuit wire, the model of the magnet, is written like this. It has the rotational speed of the magnet plus the rotational speed of the electrons when the magnet is not moving. And so we have this equation. Okay, so I'm setting the magnetic induction function to be in the z-axis direction, and using this relation, rho is in the radial direction, cylindrical coordinates. So finally, we had the force equation for the force on a conductive electron in the disk in terms of the rotational speed of the disk, omega sub d, the rotational speed of the magnet, and the conduction electrons in the magnet, actually in the closed circuit wire, which is the model of the magnet. Since the speed of the conduction electrons are usually extremely small, we do not expect the term omega SCE to noticeably contribute to the overall force, but the model does suggest there is a contribution. That is, when the disk is not rotating and the magnet is not rotating, then there is still a small force on the disk electrons, which will cause a EMF. But is it measurable? Probably not. So I'm talking about this term here is probably so small that you're not going to be able to measure it, but it is there. So now I'm going to start talking about possible motion combinations and what Weber's or my equation derived from using Weber electrodynamics is predicting. So for movement combination number 1, neither the disk nor the magnet are rotating. And as I just mentioned, there is still a force on the conduction electrons in the disk, but I think they're going to be so small that you're not going to be able to measure that. So does Weber electrodynamics predict that there will be a force on the conduction electrons in the disk under this movement combination, the magnet at rest, the disk at rest? Yes, there's still a force. No, I don't think it's going to be measurable. And I'm not going to talk about the polarity. It's not needed. When the magnet's at rest, the disk rotates. Yes, Weber says there is a force. So yes, it's going to be large enough to hopefully be measured. And likewise down through the other combinations. The magnet rotates, the disk doesn't, or they both rotate together. There's always a force. And I think these are going to be measurable. And I'll show an experiment where I think we can measure least some of those. So let's talk about this paradox. I'm not sure I understand the wording of the original paradox. Harry presented it. This is my paradox. I think the foundation of the paradox. This is a table in the upper right-hand corner showing the results, the predictions from Weber Electrodynamics, which I'll use. Okay, so we assert that this is true. The following statement is true. Force is associated with conduction electrons cutting magnetic field lines. We're asserting that that's true. Then either A, the magnetic field lines move with a rotating magnet, or, exclusive or, the magnetic field lines do not move with a rotating magnet. Okay, well, what does Weber Electrodynamics predict? Well, if you look at case number 3, when the magnet rotates and the disk is at rest, there is an EMF. There's a force on those charge in the conductive disk. There'll be charge separation. Weber Electrodynamics then predicts that there would be an EMF. Therefore, we conclude that the magnetic field lines move with the magnet so that the disk's stationary electrons can cut the field lines. Okay, but what does movement combination 4 say? When both the magnet and the disk rotate together, there is an EMF. That's shown up here, right? That's case 3 and 4. Therefore, we conclude that the magnetic field lines do not move with the magnet so that the disk's moving electrons can cut the field lines. Since the magnetic field lines cannot both move and not move with the rotating magnet, we have a contradiction or a paradox. Okay, so what's the resolution to that? My resolution is to say magnetic field lines are not real and they do not cause induced EMF. The force on an electron is not associated with electrons cutting field lines. Going back a screen, that's what this is showing. If Weber's predictions are correct, that totally resolves the contradiction. The force on the electrons, and therefore the EMF, is caused by the relative motion of the source charge bodies in the magnet and the discharge bodies. The information of the source's dynamics is communicated to the discharge bodies by the Coulomb field and the Weber dynamic coupling function. Talking about magnetic field lines can lead to contradictions when asserting that they are associated with induced EMF, as we just demonstrated. Okay, so another misconception, which I'd like to clarify, the concept is when the conductive disk rotates uniformly with the rotating magnet, there is no relative motion between the charged particles in the disk and the charged particles in the magnet. That is wrong. There is relative motion. To see this, pick a point on the disk and a point on the magnet. Is there relative motion between them when they both have the same rotational speed? Here's a diagram of that. Here's the disk electron, for example, and the magnet point. The magnet is the gray circle behind, but I'm showing it through so you can see it. Both the disk point at R position RD and the magnet point at position RM have the same rotational speed, omega. But relative motion refers to, at least in Weber, linear velocity, not rotational speed. Okay, so a few slides back, talking about all that mathematics, blah, 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 we had to convert the linear speed into the rotational speed. And that's how we did it. So this is the rotational speed of that disk point. We did the same with the magnet, rotational speed of the magnet point. And notice, if the radius to that point in the magnet is not equal to the radial distance of the point selected for the disk, then the rectilinear velocities of those 2 points are not going to be the same. And because they're not the same, there is relative motion even though they rotate uniformly together. And this is the big difference between uniform rotational motion and uniform rectilinear motion, which I show in the upper right here. Similar diagram, both the conductor and the magnet both had the same linear velocity v. Then the point velocities are the same, and you do not have relative motion. But when they rotate, even rotating quote unquote uniformly together, there is still a relative motion. Okay, another concept which I wish to clarify is when we look at this Weber-based equation for this unipolar system, notice that the force equation is not reciprocal. And what do I mean by that? That is, when the magnet rotates alone, we have this equation because omega d is set to 0, so the magnet alone is rotating. But when the conductive disk rotates alone, we have this equation. We've set the rotational speed of the magnet to 0. These two equations are not the same. It is clear that the two resulting EMFs from the reciprocal rotational motions will not be the same. Rotate the disk, leave the magnet stationary, you get some EMF. Rotate the magnet, leave the disk stationary, you get a different EMF. Now, I was reading some paper by Kelly, and I thought I didn't really study Kelly, just reading through his paper, and I thought Kelly had some experimental results that seemed to indicate this. That in some experiments, he got one EMF, and he thought he would get the same EMF, but he got a different EMF when he changed the combination of what was rotating and what was stationary. And I'm hoping that Ian will maybe point that out in his discussion next week or in a couple of weeks when Ian covers the experiments of Kelly. Because I don't know, I could have just misread that. So Ian, if you would take a note to maybe look at that in some detail, I'd be appreciative, be very curious. Okay, so here's the equations plotted out. I'm just doing a normalized radius 0 to 1, normalize the force, and you can see the movement combinations and what does Weber predict for the force on a conduction electron at a particular radius in the disk, and they're all different. So in particular, let's see if you rotate, what's that, 3 and 2. So movement 2, the disk rotates, the magnet doesn't. And 3, the magnet rotates, the disk doesn't. So here's case 3 down here in blue. Here's case 2 here in green, different, not reciprocal. What I call reciprocal. You're not going to get the same EMF in those two experiments. So here's a proposed experiment. I'm not going to read all of this. Picture is much better, but it's essentially what I think Dennis Allen mentioned a couple of weeks ago. I had this idea to use a straight piece of wire and a bunch of diodes. And then I thought about it, heard Dennis comment a couple of weeks ago. So I changed it around. Here now, you have a magnet, the big gray circle, on top of which you put a conductive ring, and then an electrical insulative gap, maybe just an air gap, then a disc or another ring. And then you hook this up through some diodes, a capacitor, some diodes, and you do the experiments, each of those experiments. The idea being that you stop all rotation. Then you take your leads and you measure to see if there's a voltage across the capacitor. Why do it this way? I'm trying to simplify all these experiments that are, to me, wicked complicated, particularly when you take a look at where are the probe leads being connected. And then you have some kind of slip rings, and then you have this, that. It's just, to me, very complicated. And the measurements are usually done while something is still rotating. So I'm trying to think of an experimental setup where you can do a measurement where nothing is rotating so that it doesn't matter how you put your probe leads. The probe leads will not couple and have induced voltages, and then you get false readings, etc. So I thought of this kind of setup. So assume that you have a ceramic magnet so that the magnet is not conductive. You should always use a non-conductive magnet, in my opinion, because if it's a conductive magnet, you're adding complexity. At least initially, let's get some initial fundamental experiments down, get them rock solid, repeatable, easy to reproduce. Then we have something to build on. Anyway, we're assuming that the B function is constant across the magnet's face. And of course, that is not true. But just, I'm trying to do some back of the envelope calculations to see, I'm going back one slide, to see if this experiment is possible at all. And so here's definition of EMF. Here's our force equation. We're going to assume that the ceramic magnet can maybe 0.4 Tesla, radius maybe 1.5 inches, rotational speed maybe 500 RPM, maybe, gives at best an EMF of approximately 5 millivolts. That's absolutely best. And then you got to subtract, oh, you're going to have losses here and there and stuff. So I say take that down by at least a half. And then it's probably not going to be an experiment that you can reliably carry out or easily carry out. But I have found other magnets. I found a magnet 0.4 Tesla with a radius of 2.5 inches. And yeah, you can go up to maybe 1,000 RPM. You can go much faster than that if you're a mechanical engineer and know how to mount these things correctly and safely. But maybe 1,000 RPM. This gives at best an EMF of approximately 27 millivolts. Okay, subtract again losses. I don't know how much losses there actually are going to be, but let's cut that out by at least a half. But hey, that's still over 10 millivolts, and you can measure 10 millivolts, particularly if nothing is rotating. So yeah, that looks, yeah, maybe you could do that. So I talked to some of my engineering guys, electrical engineering guys, and they kind of shook their head. The problem being these diodes, Schottky diodes have low forward voltage for their use, but my electrical engineering guys are telling me probably you're not going to find diodes that really operate well down in the millivolt, 1 millivolt, half a millivolt range is what you want, because you don't want these diodes to be taking up most of the voltage that you're trying to measure. So then I thought, okay, well, if I could just do this one experiment, movement combination 3, where the magnet is rotating, but the disk is not rotating. To me, that's the critical experiment. Well, okay, that you could practically just lay a capacitor over this system, rotate the magnet. While the magnet is rotating, remove this capacitor, because this capacitor is not rotating, not for movement combination 3. Take it out turn everything off, take it over to your multimeter and measure it. Yeah, you could probably do that. That's my guess. And that would give you at least movement combination 3. And that, to me, as I say, is the critical one. Because this is answering the question, does the magnetic field lines move with the rotating disk or not? Um, that would answer the, and this, when I go in a few slides and look at Müller's experiments, I think he is using the case where this actually does not produce any EMF. And so it'd be a distinguishing experiment between Weber and Müller's. And I'll show you that in a couple of slides. Anyway, just a shout out essentially to Assis and Thober. They have a paper, Unipolar Induction in Weber Electrodynamics. Their model is much different than mine. They are relying on a uniform magnetic field. They're using non-conductive. This is a thought experiment as far as I can tell. They're using non-conductive spheres. Charge one sphere positive, one sphere negative, rotate the spheres, generates a uniform magnetic field, etc. It's interesting, they publish an equation for that, and I manipulate their equation just a little bit. They do an approximation where they drop an omega square term. I leave that term in their derivation, and then their equation can be written like this, this force equation, and then I compare that to my force equation, and it's pretty similar except for I use the radius of the magnet. The radius of the magnet shows up. The radius of the spheres does not show up in this part of their equation. It shows up in their B field. So there is a difference, and I think that difference is due primarily because the way I develop the equations does not require a uniform B function. So now, let me see, we're almost at an hour. Going to take just a few minutes to talk about the Müller experiments. I'm not sure this is 100% accurate. So take it with a grain of salt. And there's some math here which I'm not going to go over. I decided I'm kind of getting tired. So I'm not going to go into a lot of detail, but there are some points to this that I want to bring out. Müller references Panofsky and Phillips' textbook, Classical Electricity and Magnetism, particularly page 148 through 151, concerning the uniform movement of the source of uniform B field. They write, the state of motion of the source of B is irrelevant as long as B is uniform. And yes, when I read that, I wanted to cry. I don't want to ever forget the source of anything. And I just don't think this, I don't think that's very good. However, this seems to be based on rectilinear motion and special theory of relativity, not rotational motion. And then I go into, well, in Weber, we drop the acceleration, we have this close in, and I'm not going to go through this other than, I'm not going to go through that. Just a counterpoint on Weber's point of view that the sources are important. Okay, so Müller assumes Panofsky and Phillips, and I think he assumes that it applies to rotating systems. And I think this is what he would have for the movement combinations, magnet and disk. And then I call it the hypothetical uniform B field, and assumed to be applicable to rotations as well. So this is the big difference here in case 3, where the magnet is rotating, the disk is not, there is no EMF. And that's because in a uniform B field, doesn't matter what the sources are doing. Okay, it doesn't matter if the sources are rotating. And this is an assertion that the magnetic lines of force do not move with a rotating cylindrical magnet. Think that's what Müller is doing. When I assume that and look at Müller's experimental results and what he claims these are the results that he has, it matches up, it works. So I think that's what he's doing. Now, P&P also writes that when the magnet is finite in width and the field is not uniform at the edges, there is then, when in motion, a change in a B field and therefore an additional E field. And Panofsky and Phillips does a little math to show that. And I think reading Müller, I think what he's suggesting is that, okay, here's a rectangular magnet. It's polarized, say, north face out. We're looking at the north face. This is in motion. You have a wire down the middle of it or laying on top of it. So the whole thing is in motion with a velocity u. And he's saying on this leading edge of the magnet in motion, you're getting a change in the magnetic induction field, they would say, and that is generating by these line of mathematics. It's going to induce an electric field. And on the trailing end of that magnet in motion, you're going to get a changing magnetic field or magnetic induction field. That's going to give you an induced electric field. And so when they're both in motion, you do not get any EMF because they are canceling. These induced electric fields due to the changing magnetic induction fields are canceling each other. I'm calling that the hypothetical edge effect, HEE, and it's applicable for translation where there is an edge to the magnet. And again, I think that's what Müller is using. But I found it very confusing. I'm not going to read this slide. It's just saying that I'm confused exactly what he's doing with that. This is what I think is happening. With these assumptions, Müller is able to explain the results of his experiments. Müller's results for a cylindrical magnet and disk are at odds with what our model predicts based on Weber. And that's a good thing. As Harry was saying just last week, I think a lot of the problems is that there's experiments that are being performed that have no distinguishing feature in their predicted results. Well, here we do. Weber, in this case 3 of motion, magnet rotates, the disk does not rotate. There's a difference between Weber. Yes, there should be an EMF or force, and therefore an EMF in Weber. Müller, I think, if I interpreted him correctly, would say no. All right, so that case 3, as I was talking about previously, we're just putting that capacitor between those two parts of that disk. That's why that experiment is so important. It will distinguish between Weber's predictions and Müller's predictions. So I look at Müller's 4 combinations for setups. And what I'm doing here is applying to each of his models this basic table. Did I click it? Oh, this basic table in the upper right, which is just for a single disk and a magnet. Okay. And then I'm using superposition to build up Müller's experiments. Okay. So Müller has a magnet rotating, this conductive wire here, IR, or this conductive wire here, ECR, and Müller gets these results. And then I look at what Weber predicts, and Weber can predict the same results. Müller, if I got him correctly with this uniform B field prediction, has the same thing, but the reason is different. The reason case 4, there is no induced EMF in Müller is because in his case 3, with the magnet rotates and the disk doesn't, there is no EMF. In Weber, Weber would say, yes, there is an EMF in IR, but there's also an EMF in EC, and so they cancel each other. So the reasoning is different. And for his block, now I think Müller is using this hypothetical edge effect. And when I take a look at that table, the upper right table in white, and apply it using the superposition principles to each of the components, again, both theories predict the same results. Let me see, but for different reasons. So here we start getting into the complicated parts of Müller's experiments, still setups. And again, I think Müller is using this hypothetical uniform B hypothesis, which is different than what Weber would use. Müller calls these steel wings. So he places some steel plates to try to encapsulate the magnetic induction field of these magnets, and he rocks them back and forth. But I think his analysis is significantly flawed. Excuse me. And this is why. I think he's forgetting that the steel plates, again, I wasn't there. I don't know exactly his setup. I don't know exactly what he's doing. But I think these steel plates are conductive. And so if you're rotating, even just rocking the magnets back and forth, you're going to get charge separation in the steel plates. Okay. And if you have a wire on top of that, and I'm not saying in contact, but in the vicinity of, as I show here on the right, this EC, that's this EC shown on the left, there's a charge separation as the magnet is oscillating, and it's going to oscillate from plus to minus and minus to plus. It's going to oscillate. That's going to induce electric charge buildup. Electric charge buildup has an electric field. The electric field is going to cause electrons in the EC wire to move. And if you've connected that to, your meter, it's going to register that. And there's some experimental evidence, which I will show at the end, in support of this interpretation of what's going on. So if you include that, then yes, Weber and Müller's case predict the same thing, but I think for different reasons. I just don't like his analysis. He doesn't mention, as far as I can tell, this charge buildup here. He just says that, this ECR is not in a magnetic field, and therefore there's no induced EMF when that part of the circuit moves, and he's not taken into consideration this charge buildup due to the magnets moving. So in this case, where it's rectilinear motion, again, I think he's not analyzing the situation correctly. And this is why. So while this magnet is moving, I think it's causing a charge separation across the plates. That, and which I'm showing here. Again, he has a wire over that, and therefore it's in the electric field of these charge buildup. And that's going to cause the electrons in this EC wire to move. And that's going to be detectable or not, depending on if there's other EMFs that's happening. But I don't see him mentioning these charge buildups. Now, let's take a look at this and think about it carefully, because I'll show you experimental evidence that this is the case on the next slide. But I want to think about it first here. So we take the square magnet, we move it all the way over to the left. We're about to start the experiment. The magnet starts to move from the left side here over towards the right. Okay, it's in uniform motion while it's moving. Okay, but to start moving, it has to accelerate. While it's initially accelerating, it's going to cause this charge separation in the steel plates. Once the magnet is in uniform motion, the charge separation is like in a static equilibrium because now it's uniform motion. Okay, and then at the end, it has to decelerate. And when it decelerates, these separated charges in these steel wings recombine. You got charge motion again. You got a changing electric field, which will redistribute the electrons in this part of the wire, EC. Okay, but during the uniform motion, that movement of all the charges in this wire EC has already happened. There's no additional movement. So during the uniform motion, there's no measurement of an induced EMF. Only during the acceleration and deceleration, when the charges are separated initially and then recombined, yes, you'll get an EMF in this EC wire or in that circuit ECR, etc. Experimental proof, in my opinion. Müller's 2014 paper, he published this graph, and he says all the components, IR plus ECR plus the magnet, move together. The arrows indicate the start and stop moments of the measurement. So here is his arrow. He starts here and he ends here, the measurement. Right at the start, he sees a spike. During the uniform motion, he says maybe some noise, maybe it's not moving quite uniformly, maybe it's noise. And then at the end, decelerates and he gets a spike of the opposite polarity. That to me is signaling what I think is the experimental confirmation that he is getting charge buildup on the edges. The charge buildup has an electric field. The electric field is interacting with this EC conductor and the rest of that, circuit, CR, causing the electrons to move within that conductor, causing an EMF to be registered at the beginning and end of his motion. So that's my presentation. Here's a few conclusions to review. We have shown how to develop a mathematical model of unipolar system using Weber electrodynamics. The development started with fundamental facts and used Ampere's and Weber's experimental results encapsulated in Weber's force equation. The Coulomb field is the physical field. Extraneous postulation of other physical fields was not utilized. That's an appeal to Occam's razor. We resolved the paradox of magnetic field lines or magnetic lines of force rotating or not rotating with a magnet. We've clarified the meaning of relative motion for rotating systems. The resulting model and proposed experiments provide means for validating the model and selecting the appropriate theory. The non-reciprocity of the induced EMF for the three cases. Different motion combinations predict three different experimental results. Another way to hopefully validate the theory or not. And this is a different prediction than the theory we think that Müller is using. The results of the four experimental designs of Müller was used to explain using Weber and electric charge buildup. And that's my presentation. Thank you very much. Let's have a discussion.
Well, that was certainly a very stimulating lecture and very impressive in the amount of detail that has been gone into by Bob. I think we do have a good amount of time now, despite the fact that Bob was a little worried about the extent of his slides and whether he'd be able to get through them without rushing too much. I think he did an admirable job at that. I just maybe have a few little comments, maybe to set the ball rolling, and then we can open it to discussion. I have a couple of questions we might try to deal with first, and then we'll perhaps try to get a number of people up in the green room. Well, I'm extremely interested in this, and I must say, possibly, even though I'm a dissident scientist, I would call myself such. I do start from the impediment of, accepting more or less the Maxwellian electrodynamics, and therefore, it appears to me in certain circumstances that although the Weber alternative is interesting, it contravenes Occam's razor to a certain extent. It seems to be introducing a lot of perhaps unnecessary hypotheses, but we could argue about that. For example, and Bob may wish to comment back first before we get to some of the other questions. But the question of whether the field rotates with a magnet or not seems very fundamental to me. And maybe to say it isn't a problem now. You get contrary results by applying different experiments or different theories. But we just resolve the thing by saying there's no such thing as magnetic field or magnetic lines of force. That seems a bit of a cop-out, if you forgive me. Now, the other thing about explaining things by saying, well, there's no angular relative motion, but there is linear, because at different radii you get different linear. That seems a bit contrived to me as well, if you forgive me. So I'm being very skeptical about the whole theory. And therefore maybe the explanation of the asymmetry in regard to things which otherwise would appear to be symmetrical. Although I must say that this innovative experiment, which I had a preview of when Bob was kind enough to present me with the germ of his idea, but he's now developed it with diodes and one-way electricity and all that, about trying to exclude the leads taking back any current to the galvanometer, would appear to me, very much worth doing. I mean, Harry said in his lectures that the experiments have been thrashed through so much that there's no point in doing any more. We have all the parameters, and we just need to have a theory. But I think that is one experiment which actually would be well worth doing. Bob's ideas, of these sort of wheel spokes and diodes and all that. If I may be a little critical again, the hypothetical edge effect seems to be a bit contrived as well. And the Panofsky and Phillips table seems to contradict some other tables, as indeed Bob has pointed out. He was comparing Weber with Müller and so on. And my last point is, well, I've already mentioned the thing about the lines not existing. Now, just before I give the floor to everybody, I just say that there'll be an alternative way of looking at this, maybe, which is Kelly's way, which Bob has kindly enough said that he's extremely interested in. In fact, I must just take the opportunity of just making sure I understand this point. He was talking about the let me see, the two cases which would appear to be symmetrical and indeed are not, and he's looking forward to my explanation of that when I deal with Kelly's experiments and maybe the germ of a theory which might be based thereon in 2 weeks' time. So maybe in addressing some of my points, you might wish to make sure that I do understand that, Bob, so I can deal with it, and then we'll deal with the questions. So back to you, Bob.
Well, I appreciate all your comments. And would love to go into in-depth discussion on all of the points. Not sure where to start. I tried to show that for the paradox and what I call the paradox and the whole development of this Weber force equation, I wanted to show and try to get the feel across that we're starting with almost nothing. Just a couple of facts. I got a charged body and a charged body. Okay, I don't see anything wrong with that. Charged body interacts with a charged body. Okay, I don't see anything really wrong with that. And according to the experiments, we can deduce an equation, Weber's equation. Well, okay, it's consistent with all those experiments, so we'll assume that that's appropriate for at least these experiments. If you go that far, everything else is a mathematical derivation. And if you believe in the mathematical derivations, and okay, a lot of approximations, et cetera, you come to this result, this table that I'm showing. And this table is contradictory if you use and try to explain these things with lines of force. If you use that a force is associated with conduction electrons cutting magnetic field lines. Okay, so what part is causing that contradiction? The mathematical steps? Well, that's mathematical steps. I'm not the world's greatest mathematician by any means, but I don't think there's a mistake in the mathematical steps. So what are we, and the starting point was not, hey, we got field equations, all these Maxwell's equations, field equation, we're assuming those are true, and we're going to, adopt in the Lorentz force, assuming that's true without looking at where that's coming from and where it's applicable and where it's not. A lot of my equations you might see, I try to put the restrictions for applying that equation. I'm a big, proponent of doing that kind of thing, particularly because of that Lorentz force equation. I have no idea when that's appropriate to use and when it's not appropriate to use. And it's confusing. And the textbooks don't mention that either. So anyway, for the paradox part, what are we to do? If we go with the starting point, the mathematical steps, we get this paradox or resolution if you give up the idea of cutting magnetic field lines.
Okay. Well, perhaps just before finishing that, we might be able to deal with one or two questions, Bob, here related.
Sure.
Yeah. So just Dennis has just added in regard to the Lorentz law that J.P. Wesley says that in general it does not conserve energy. In fact, I think nor does
That's
it
right.
comply with Newton's third law. And
Right.
I just said that's also what he says in Biot-Savart. So you just
That's right.
concur with that, do you, Bob?
Oh, I agree with that. It does not. It does not conform to, let me see, I think also angular momentum.
The conservation of angular momentum. Okay.
Yeah, anyway, it fails the Newton's laws of motion, action and reaction, etc.
Okay.
That force law does not
So
comply
maybe
with
that
those.
gives us a bit of a warning that it has limited applicability. It is not totally general.
Well, my big question for that equation is, does it apply to individual charged bodies? Where does it come from? In my reading of what little history on this I've read, it comes from integrating Grassmann's force equation around a closed circuit. Well, then how can that apply to an individual or two interacting individual charged bodies? It can't. I mean,
Yeah,
that's
that's back to the Biot-Savart law.
yeah. So it's anyway.
Okay. So just a very specific point, which somebody asked in your diagram about these Amperian current elements, are they still moving? Do they move as well in your system?
The Amperian current elements, let's see, the elements overall can move because you can translate any of these things. Individually, it's the positive charge and the negative charges which move in any particular element. But then you can translate the whole thing by adding a velocity to each of these.
Okay, so in general, I suppose
That's
the answer
why you take this conductive wire and you bend it into a closed loop, is where I was going with this. Make it into a closed loop, and then you can rotate that loop. So yeah, the individual ampere and current elements can rotate with that whole rotation. Or this current loop can be stationary, and you still have the current, which is the conduction electrons flowing around in the loop. I think I'm just confusing people, but
well, sum up. We can come back to that in discussion. There is time for people to come in, and on the green room, I will be inviting people in a moment. But I just have about 3 more comments to deal with, and I think some of them can be dealt with in one general point. It's been asked, Bob, could we have a press copy or slides or something? And people are saying, oh, it's so quick. So I have pointed out that this will be recorded and will be available in perpetuity on YouTube for people to rehearse and stop at any section or copy anything. But more generally, is there any reference? Have you yourself written a paper, or is there anything, any paper you might give us a reference to?
by the way, you can always reach me by that email address here.
Okay.
I have published a couple of things on what's it called? It's been so long now, I don't remember. Having a senior moment. I don't remember. There's a place where we publish papers, not journal papers necessarily, but I forget where it is. And then if you
anyway, the bottom line, you have a website as well, which is based on a similar.
This is my book. I do not encourage people to purchase this book. This book was more or less an exercise that I did to figure out how to publish a book. This is full of all the detailed calculations that I have done in Weber Electrodynamics. There are some things in this book now that I kind of cringe at, and I should update. I do not recommend anyone purchasing this book. If you really are interested in 300 pages of calculations, send me an email address and I can send you a PDF of this. The second one, I thought I would get rid of the derivations and just kind of present results. And I think that came off a little bit better. Again, don't spend any money on this stuff. This is essentially a paper. Most of it is a paper which I published or put out on that repository, that site, which I can't seem to remember at the moment. Scholar or something.
Google Scholar.
I can't remember.
Well, maybe I could just alert the audience to this, my own experience. I mean, you said during the lecture, Bob, that you were not sure if you were a very competent mathematician, but I would beg to differ. I mean, I have some personal experience when Dennis Allen and I were drawing out some equations based on Wesley's distinction between the energy and Poynting vectors in
right.
You remember that longitudinal versus transverse radiation.
Sure.
Denny gave me a general, derivation and so on, and I worked a bit further on it. I just lost patience. I think I'm reasonably mathematically competent, but I lost patience. I just gave up. But you actually we presented the thing to you because we had some discussion about this, Denny and I. Yep. And you just went through and gave me the general case. You wrote a few pages of mathematics, and right. I don't think I would have had the patience to do it. So I was very impressed with that. So you're putting yourself down a bit. But I would say that only take your advice not to get those books if you're not very mathematically competent and inquisitive. Now,
Because that's all that it is, as I say. They are
Yeah.
my derivations, my notes on how I derived all this stuff in Weber electrodynamics. I try to do a comparison with Maxwell and show where that kind of fails, in my opinion, etc. And I try to put, for example, Weber in terms of what might be Maxwell-like equations, which I have here, the divergence of these, the curl of these fields, etc. This is for discrete individual charged bodies, and I tried to do it with the current densities and charge density functions, integrals as well. The results are interesting. I see a lot of similarities between Weber and Maxwell, but there are just differences. For example, here in this equation, it's the Coulomb field, not the general electrodynamic field. Okay, and then in the divergence, it's the Coulomb field again. I can mathematically derive these equations. Given Weber's force equation with the coupling coefficient, I can derive these equations. They're very similar to Maxwell, but not exact.
see,
And again,
would
I don't
argue-
know Maxwell, how to express Maxwell in terms of individual distinct charged bodies. That's one of the problems I have with Maxwell's equations.
I was interested also in, you're introducing this sort of B, which is not the same as Maxwell's B, magnetic induction or flux density.
Right.
So it appeared to me, for my part, I don't know if this is totally accurate, that whereas in Maxwell, he would give sort of an equal weighting between the electric field intensity and the magnetic field intensity, in Weber, it's the electric field, which basically is the fundamental, and
Yeah.
the other one almost doesn't exist. It's just a consequence. So
Right.
it's a different way of looking at it.
One
Okay.
of the big differences is in this definition here is using an Amperian current element, which means that there are two velocities, not one. It's a velocity difference. And that is what I think is lacking in Maxwell's electrodynamics. The way they define current density is usually a charge density times a velocity. Well, no, that should be a velocity difference. That's the big difference.
Okay, because I think people coming to this afresh frequently see, a velocity term in the basic Coulomb type electrostatic force when you're dealing with Weber,
Right.
whereas that's absent. So that's where they
That's
actually
right.
start from.
Yeah.
Okay. Now, is there anybody? If there's anybody in the green room who'd like to say a few words, just wave your hand, and I'll bring you up. As David Hilster does, he invites people in. I see Harry is there. I hadn't seen you, so I'm going to bring you up now, Harry. I'm glad you're here. First of all, yeah, you're unmuted. How do I bring you up? I'll try. There you are, Harry. Have you been around at all? Because we didn't see you at the beginning.
I watched on my big screen TV. It's better than sitting here in front of this teeny computer.
Excellent. Good.
Okay, I have a couple of comments, and so we can sort of clean this thing up. One of my comments is that what's in dispute, I see from Bob Gray's presentation, is just exactly what the experiments show. And I think that's really one of the main points of this exercise, is to kind of come to some kind of agreement as to what the experiments demonstrate. And I think Bob's sort of at a disadvantage because he's not really sure, because he's basing a lot of his analysis here on what Müller did, and he's kind of skeptical or confused by what Müller did. But what I think is that if you start comparing all the different experiments that have been done by different people and going through it, you can basically come up with what really basically the experiments do show, and because they will agree. And I think that's one of the things that we ought to determine moving forward.
Yeah, I think that's a good idea. The only downside to that I see is experimentation is messy. That means you got slip rings, you got other sliding contacts, you got lead wires coming, and depending on where you put the lead wires, depending on are they shielded, not shielded, it seems that people get different experimental results. So I'm not competent enough to be able to sort through all that and say, oh, well, that was because he had a lead wire connected this way. He should have had the lead wire connected the other way, and I just don't know. So
My
I'm
area of
hoping,
expertise.
yeah, I'm hoping an expert, would help with that.
Well, I think that's one of the things that I'd like to be able to clarify. And I think when we talk about Al Kelly's experiments, essentially what happens is most of these experiments do agree, except in cases where people try to make out of the normal claims. But most of the experiments do agree. It's just a question of establishing exactly what those agreements are. And because, like you're pointing to Müller and saying, well, I didn't really understand what Müller did. Well, if you go and look at other people who have done similar experiments, it becomes a little clearer, and
Sure.
you gain confidence in what Müller did and what his results are. So you gain confidence by comparing different experimenters. The other thing I wanted to mention was that regarding your experiment, I think that's already been done. Okay.
Great.
And the result has been negative, but you can sort of critique the particular experiments and the method used in those experiments, because they didn't do it exactly the way you proposed it to be done by having the discs and measuring the EMF between the strips and the two discs. You have two annular discs basically, and you're measuring the voltage between them. These types of measurements have been done, but not in that particular configuration, and they've been null results. But if to resolve your difficulty, there's a device called an LTC 2053, which I believe is an analog devices chip. And that was used by the guys that did the experiment that I talked about 2 weeks ago, where in the refuting Faraday's paradox presentation I gave, and they use this device. Now, this device has got an estimated input impedance of about 4 megohms, which is very high. And it also has a capacitor input. And so what it does is it has a capacitor, and it basically detects the charge on the capacitor, and it's got a switching device that then transfers the charge on the capacitor to an operational amplifier that measures the voltage that's appears across the input capacitor. So this device should be capable of doing your measurement for your experiment. Now, they used this device in their experiments and, of course, got 0. All of the experiments that have been done to detect an EMF in the configuration that you're proposing in your experiment have come up with 0.
Wow, that's amazing and exciting because that essentially refutes Weber, or at least the model that I've developed, and I want to know that. Wow.
Well, I alluded to that last week but I didn't really go into a lot of detail. Now,
one of the things that you mentioned, Bob, was that even when you would otherwise get a sort of a zero effect. There were very, very small residual effects from the Weber theory, if it were correct, that perhaps couldn't be measured or were too small to measure.
Right.
Yeah. By the way, Harry, if I'm just made before you go, there was a gentleman, I think Toby Grotz, if I'm pronouncing his name correctly, that I think he asked a question last week. And he put a comment up here, how can I get in touch with the previous speaker? So I said, do you mean Harry Rooker? He didn't respond, but he's responded now. He says, yes, he wants to get in contact with you. So how can that be done? Do you have any...
All right, I've got some kind of interruption here.
Oh, okay. It's just that somebody has asked for your contact details.
All right, I've already exchanged emails with him. I already exchanged emails with him.
Okay. Well, I don't know why he's asked again. Okay.
Maybe he forgot, but I sent him a reply. He sent me an email, and I sent him a reply. Maybe he didn't get it.
Okay.
He has my email because I did receive an email from him.
Okay. He probably got that from the database or something like that.
Okay. Well, I did get I did get an email.
He says thanks now,
and I replied to it. He didn't reply to my reply, so I'm not sure what happened there. But
well, I think he says he'll look at it. I think he'll probably get a reply now. That's one of the advantages of having these face-to-face meetings.
Okay. Now I do want to comment again from an experimental point of view on your criticism of Müller's experiment there, and where you were talking about where he has the shielding. He essentially basically conducts the magnetic field away from the wire ECR, if I get the nomenclature correctly. So there's no magnetic field at the location of the wire ECR. And you talked about you have an alternative explanation. Now, I do want to point out that there have been other experiments where people have used superconducting tubes, okay, and other, Wally Verderde, or whatever his name is, I can never pronounce, this Argentinian guy did a bunch of experiments in which he also attempted to shield the magnetic field from what he calls the closing wire. Some people call that wire the ECR wire, the closing wire. The terminology is different for different experimenters.
Okay.
And basically all those experiments basically give the same result as Müller's result.
Mm-hmm. Good.
Okay, so that's something that you can
now. I think I commented on this, and I have a little paper called Unipolar videos. If people are interested in that deals with videos that appeared on YouTube. And I sort of talk about the videos. Some of the videos have mistakes in them. I point out some of the mistakes that they made. So if you're interested in unipolar videos, kc3mx@yahoo.com, you can send me an email. This isn't published. It's just a paper that I have in my computer. I also have another paper published for.
Sorry, you just went off there a second.
Out, kind of, I gave this information when I was going to give my talk 2 weeks ago, but then the talk got delayed a week. And when they sent out the invitation, they neglected to send out the supporting information that's contained in these two papers. So if you're interested in this information that goes along with my original video of 2 weeks ago, you can send me an email.
Okay, and Franklin has put up the email also of Bob, which I think you had. So, so is that
I
everything?
think the bottom line is, just before I just want to finish up here. I think the bottom line is that we know what the experimental results are because of all the different people who have done the experiments, and they're all pretty consistent in what they show. And interestingly enough, they all pretty much agree with what Faraday came up with originally. But what I find is that Müller apparently talks about Faraday, but he didn't read Faraday's book, from what I can see, because he sort of says things about Faraday that aren't really correct, which imply to me that he didn't read Faraday's book, or if he didn't he didn't understand it. So it's interesting that all the results that have been done pretty much agree with what Faraday did.
Good.
Oh, okay, thanks very much. And it's obviously the interpretation of that, because I would agree with that, and I'm hoping when I deal with Kelly to indicate how he proposed some differences, although fundamentally he agreed with the concepts. Now, Franklin had some further. Yeah, James, I'll bring you in a second. Just trying to get Harry down. Well, he's got himself down. Franklin just had some further question about this velocity difference, and he's questioning how that's going to be so. Would you like to say something about that, Franklin?
Yeah, I'm still trying to understand what this ACE thing is. I mean, he's treating it like a dipole, and he's saying that, there's a velocity difference between the positive and negative, but the conventional picture is that, the protons are stuck in place in the wire, and it's the electrons are moving, and, the protons and electrons do not ever go together in a packet. So I was just kind of wondering, Bob, what does that actually mean? Because that just doesn't really make any sense to me.
Yeah, it's the electrons that are shuffling around, but they leave behind the positive ions. So where I'm showing these pluses, I'm not saying that the pluses are moving. I'm saying that the electrons are moving away from the pluses to leave the pluses there. Same within this EC wire. The wire itself is full of plus and minus charges. The minus charges, electrons, move away, leaving the pluses behind.
Although in a wire, they're also getting closer to the other pluses. So there's no, net difference, right? You have a whole bunch of negatives going by, a bunch of sitting positives, then I would think all of that would cancel out. Is it?
Well, it's 1-to-1 in the neutral state, one electron, one positive ion. Now, if I move that electron, that's going to leave a positive ion there exposed.
Except that another electron will take its place.
But that's where the EMF comes from. It's saying, I can't. The electron says, I got to move to the right, for example.
Yeah, but another one, like I said, will exactly take its place, right, from the left.
Until there are no more to take its place.
Well, there are always more to take its place in a
there's in a finite, piece of wire of a certain length. I can shove all the electrons towards one end.
Yeah, I think maybe that's the difference between dealing with a single piece of wire, where you can do that, and a circuit. I think there's something about a circuit here. Yeah. Now, usually the only way we can measure this thing is actually in a circuit, that we can't measure.
Yep.
Usually all electrons piled up on one end of a wire, I guess.
And by the way, this is something that I'm hoping to say something about, the contrast between a closed circuit, which indeed has been referred to by Bob earlier, and the application to non-rigid, closed, open elements, if you like. So how induction affects those. It's a non-zero effect, I think I'll be maintaining. So is that okay for Franklin, or did you want to leave it at that?
No, I think that's fine.
Okay, thank you very much.
James wanted to make a comment here?
Yeah, that's right. James, bring James up. Can we bring James up? I don't see how you do that. There he is.
Okay, you just on his picture there.
The floor is yours, sir.
Hello.
What's that? NYC, New York College, is it?
Thank you, Bob. Well, I have the baseball cap on for a reason I'll explain in a moment. I like Bob's presentation. Thank you, Bob. And I like the introductory part where he was saying it's not necessary to keep not necessary items out of theories and to build on things which are presumably necessary. Now, in this context, I'd like to point out that the mother of all the theories which are questioned by the dissidents here, whether it's special relativity or anything else, Maxwell or any of these others, is the continued assumption. This is the mother sow on which all these little piggy theories, which everyone finds flaws with, is based. Oh, okay, that's a little editorial comment. Now, from the baseball stands, I'd like to throw onto the field an empty Coke bottle for Bob and ask him to comment on magnetic monopoles. They exist, they don't exist, etc. Whatever. Thanks.
I think they do not exist by definition.
Okay, I threw my Coke bottle.
Okay. Well,
what
this
was
an
that, Bob?
interesting
I didn't hear that.
Sorry?
I don't think magnetic monopoles exist by their very definition. However, you can conjure up, put things together. I think Franklin demonstrated this at one point, and it's as if it were, or it's similar to or like a magnetic monopole, but it's not really a magnetic monopole. That's my 2 cents on that.
Could this be like the fridge magnet that Bill Lucas talked about?
Monopole,
Yeah.
Yes?
Yep.
Okay.
So we're excluding tiny particles, which we might call magnetic monopoles, which physicists have been wondering about for a long time, since the discovery of positive and negative charged objects. So I threw my Coke bottle there, and whatever comment you want to make, fine. Thank you.
Okay, you're breaking
Thanks,
up a bit,
James.
but I think we got that.
Thanks, James.
Okay, so basically, I suppose you're accepting that Maxwell's equation that the divergence of the magnetic induction vanishes.
Yep.
Right. We had actually Jerry in today on the Green Room. I think it's the first time he's appeared on the Green Room. So would you like to say a word or two, Jerry, briefly?
Yeah. Well, I have one main question that I have written down here. Can you hear me?
Yes.
Go ahead. Yes. Here you
All right, cool. All right. Why did Einstein combine the electrodynamics of moving bodies with a sort of neutral system of the dynamics of common objects, observers, and light sources, all relative to each other? Does special relativity actually account for each of these clearly different aspects of reality? Is it possible that Einstein may have applied too much electrodynamics knowledge that wouldn't work exactly well, or at least as accurately, with kinematics? Would electrodynamics play by different rules than kinematics?
That's
Okay,
interesting.
would like to say a few words about that, Bob?
Yeah, I don't know what to say exactly. It's an interesting thought. I think Einstein could have or should have looked at the basis of Maxwell's electrodynamics, found flaws to that, and wouldn't need, for example, what I'm advocating is changing the basic definition of a charge and a current density function. And if you look at the Weber electrodynamics, which has that different definition of a current density function, then the asymmetries that Einstein was talking about, I don't think exists. And therefore, I don't know that he would have gone on to developed the special theory of relativity. I don't know.
Yeah.
Yeah. Well, wasn't the sort of original, like where he derived a lot of it, like at the beginning of his original paper, where he had said how with the current being made with a wire, and then there's a magnet.
Magnet, right? Yeah,
That
exactly.
if a magnet is in motion, it creates. Yeah, if a magnet's in motion and the wire is stationary, then it creates the current. But
Right.
it doesn't work the same way if the magnet is stationary and the wire is moving.
Right. And I think Weber says yes, it would be the same. And the source is not magnetic fields. The source is a difference in the velocities of the charges. You got the charges in the wire, the charges in the magnet, and it's their relative motion that's causing all this. But the big problem, I think, in Weber electrodynamics, when you talk about special relativity and Einstein, is I think Einstein is talking about light. Weber electrodynamics does not go that far. I don't see light in Weber electrodynamics. What's the definition, or how do you derive a light beam or a wavefront? What is light in Weber electrodynamics?
Well,
no clue. I don't have a clue on that.
Yeah.
And that's in my opinion, a big hole, a big failing of Weber electrodynamics.
Well, also Einstein did. I mean, what Einstein's original idea that he was analyzing to arrive at special relativity somehow, that light isn't mentioned with the experiment of the electric current with the magnet and the wire. That light isn't mentioned there either.
Yeah. Interesting.
Do you see? Some researchers have used the apparent paradoxes of the
Bob,
Faraday
you
generator.
think
Sorry,
magnet?
sorry. Could I just finish the sentence, please?
Why are we magnet? If there's no magnetic field.
Sorry, James, you've just introduced something else. Could I just finish my sentence, please? Can you hear me?
Yes, I can hear you.
Some researchers have used the apparent paradoxes of the Faraday generator and so on to
prediction went off.
James, you're just coming in the middle. I don't think we have time really to go into a separate thing, but I can keep myself quiet and let you come in, or let me finish, please, my sentence. Repeat it again. So what they've done is they've used these paradoxes to try to discommode the relativity, in particular the special theory of relativity. They might have had an ulterior motive on that, but I think I'll be explaining maybe in a couple of weeks' time that I would take all of these induction experiments to be compatible with classical relativity. And as far as I can see, Bob was probably effectively doing the same thing. I mean, he did mention the sort of relative motion of these bodies or these charges. So unless there's anything very, very pressing that James wants to mention, it's probably time for me to summarize. You didn't want to say something very urgent there, James, did you? That I cut you off on? No, I wasn't sure what that was. Okay. Well, I think, as the lawyers say, res ipsa loquitur, the thing speaks for itself. I think this lecture spoke for itself.
No, go ahead, Ian.
Yeah, there's a bit of a delay of about a few minutes, James. Okay. So I think the lecture spoke for itself. Any small words of mine would not really add much to it. All I can say is, for my part, I found it very, very interesting. I found the theoretical basis quite illuminating, because I always like to have a balance between theory and experiment. And he obviously gave the basis to the Weber analysis insofar as Bob has done the research and then applied it to a specific case, which actually is quite refreshing, because frequently it's the other way around. The experiments are sort of talked about, and then you introduce the theory. And for my part, I have asked before, what is the whole big thing about Weber electrodynamics? Because I'm more conversant with the Maxwell equations, and I know these added velocity and acceleration terms and so on. So I looked at it as an alternative, but I think Bob has given us a succinct reason why it might be fruitful to go in a bit more detail to the whole concept of Weber electrodynamics. And of course, Weber actually did work with Gauss, and they were the first really who introduced the electric telegraph. So these great theoreticians had done work which resulted in very practical affairs. So all I can do is on all your behalf, I'd like to thank you all for your questions and your contributions in the green room, and for keeping the thing succinct and allowing Bob to have his almost 1.5 hours. Actually, he finished a bit early, so we did have a good half hour for Q&A, but not long enough. We'll be returning to these subjects again. And in fact, if you haven't had enough with Harry and with Bob, you're going to have me again in 2 weeks' time, where I will be looking at Kelly's experiments and hopefully trying to clear up any darkness that has been expressed to me with regard to the understanding of those experiments and Kelly's proposal for maybe a more universal theory. So the announcements will be made in due course by David de Hilster. Provisionally next week, we'll have one of the standard meetings, which I think will be concerned with maybe lifetime awards and so on. So you'll hear more about that. So keep posted and look at your emails and look at what's being offered. And we hope to see you next week. And provisionally, as I say, announcement will be made on the 17th with Kelly's experiments and unipolar induction by yours truly. And Franklin has very kindly agreed to host that in my absence. So he'll do everything technical and administrative. So without further ado, I'll wish you, wherever you are in the world, a very good day. And thank you for your attention.
Thank you, Ian.
Now.
Thank you.
You're very welcome. Thank you, Bob, again.